let's begin our very last section of chapter 10, which is dealing with the calculus of polar curves. So first off, we're going to work on calculating slope, and try to remember slope is rise over run. No matter what type of format your equation is written in, rectangular, vector, parametric, or even polar, slope is always rise over run, which is dy dx. So basically, in polar form, slope is still dy dx and not dr d theta, like some people will mistakenly identify. Okay, now recall that x equals to r cosine theta and y equals to r sine theta, and our equations is going to be basically an r equals to something kind of an equation. R equals to f of theta, a function in terms of theta. So sometimes these are rewritten to look like x equals to f of theta cosine theta and y equals to f of theta sine theta. Now, in order to find slope, which is going to be our dy dx, because x and y are not written in terms of x or y, they're written in terms of theta, we're going to have dy d theta over dx d theta. Kind of like with how parametrics we did dy dt over dx dt, we're going to do that same kind of thing here. But because f is a function in terms of theta and it's cosine of theta, another function in terms of theta, we're going to have the product rule. So the derivative of y with respect to theta will be f prime of theta sine theta plus f of theta times cosine theta. That's using the product rule. And then all over f prime of theta cosine theta, now minus f of theta sine theta. And it's a minus down here on the bottom because the derivative of a cosine theta is a negative sine theta. So our first example, we're going to, for the function, polar equation, r equals to 1 plus cosine theta, where the theta interval is given as 2 pi, so I want theta between 0 and 2 pi. Actually, I first want us to find when dy d theta is equal to 0, and then subsequently find when dx d theta equals to 0. So let's take a look at dy d theta. dy d theta means we have to take the derivative of y, and since y equals to r sine theta, I know that y equals to 1 plus cosine theta sine theta. Now where'd that come from? Well, we're taking this as our r value and plugging it in. So then I'm going to take the derivative with respect to theta, and I'll do the product rule. So I'll get negative sine theta times sine theta plus 1 plus cosine theta times cosine theta. And I'll need to solve for this when it equals to 0, so I have negative sine squared plus cosine theta plus cosine squared theta. Now here we have to do quite a bit of trig work. I'm going to need to set this equal to 0, and in order to solve that, I'm going to replace negative sine squared theta with a cosine squared theta minus 1. That's using my Pythagorean identity. So when I gather everything all back up, I have 2 cosine squared theta plus cosine theta minus 1, and I can factor this. 2 cosine theta minus 1 times cosine theta plus 1. So since this is set equal to 0, I know that cosine theta has to equal 1/2, or cosine theta equals to negative 1. So cosine theta equals to 1/2 when theta equals to pi over 3, or 5 pi over 3. Now this is off our unit circle. And cosine theta equals to negative 1 when theta equals to pi. So our interval was from 0 to 2 pi, so these are my three answers. At these three theta values, dy d theta equals to 0. So then I'll go back up, and I'm going to do a similar kind of thing for when dx d theta is equal to 0. So this time I'm going to use x equals to r cosine theta. So therefore x equals to 1 plus cosine theta times another cosine theta. And when we take the derivative with respect to theta, I get a negative sine theta cosine theta plus 1 plus cosine theta times a negative sine theta. So let's multiply those together and clean them up. I'll have a negative sine theta cosine theta minus sine theta minus another sine theta cosine theta. So I have two of those. Now I need to solve this for when dx d theta is 0. So I'm going to factor out what they have in common. And either sine theta equals to 0 or cosine theta equals to negative 1/2. So theta equals to 0, pi, or 2 pi. And for cosine theta equals negative 1/2, I have either 2 pi over 3 or 4 pi over 3. So those are my solutions when dx d theta is equal to 0. So I have one more question. We're going to continue this a little bit more. I'm going to want to know, when do we have vertical and horizontal tangent lines? Okay. So now when do we have vertical tangent lines? Vertical tangent lines exist when dx d theta equals to 0. So in this case, when theta equals 0, pi, 2 pi, 2 pi over 3, and 4 pi over 3. Those are all the angles listed above. And we should have horizontal tangent lines when dy d theta equals to 0. So that would mean pi over 3, 5 pi over 3, and pi. So should that be our answer? Now I need you guys to take a look at something. What do you notice? Pi shows up in both of these. Is it possible to have a vertical and a horizontal tangent line at the same time? Actually, no. So what this is telling us is that dy dx, which is our dy d theta and our dx d theta, is a 0 over 0 when theta equals to pi. This is an indeterminate form. So what's going to happen is we're going to have to use L'Hopital's rule. We need to figure out which one is it exactly. So whenever you calculate your dx d theta and dy d theta and have the same angle appear in both, we need to calculate the limit as theta approaches that particular angle of your slope and evaluate it. So in this case, I need dy dx, and up above we have our dy on the left side and our dx on the right side, and we need to just pull any one of those forms and evaluate it. Okay, so you can look above into your own notes. I'm going to go ahead and write in 2 cosine squared theta plus cosine theta minus 1, and divide that by negative 2 sine theta cosine theta minus sine theta. Now I'm actually going to choose to rewrite this as a sine 2 theta. So this I know was 0 over 0. So I'm going to use L'Hopital's rule and take the derivative of the top. and then the derivative of the bottom. And we're going to evaluate this as theta approaches pi. So now when theta approaches pi, the sine values are 0. The cosine values are not. So I know that this limit equals to 0. So what does this mean? This tells us that dy dx equals to 0 at theta equals pi. So we get to go back up, and our slope is 0. So that means we're going to have a horizontal tangent line and not a vertical tangent line. Okay, I'm going to continue this and ask another question with this same problem. I want us to write the equations of the vertical and horizontal tangent lines. So I actually want the equations of those lines. So since we know x equals to r cosine theta, so x is 1 plus cosine theta times another cosine theta, I want us to find x when theta is 0, 2 pi, 2 pi over 3, and 4 pi over 3. This will give us our vertical tangent lines. Now for the horizontal tangent lines, oops, let me write vertical here. And for our horizontal tangent lines, I'm going to use y equals to r sine theta, which is 1 plus cosine theta times the sine theta. And I want us to find y when theta equals to pi over 3, 5 pi over 3, or pi. So again, two separate things that we're looking at. So I know that x equals to, or actually x when theta equals 0 or 2 pi, because those are actually in the same spot on our unit circle, that equals to 1 plus cosine theta times cosine theta. So what is cosine 0 or cosine 2 pi when we plug those in? It equals to 1. So I have 1 plus 1 times 1, or 2. So my equation is x equals to 2. Then we move on down the line and do the other angles. We want to find x when theta equals 2 pi over 3. So that's 1 plus cosine 2 pi over 3 times cosine 2 pi over 3. So cosine 2 pi over 3 is equal to negative 1/2. So we end up with x equals to 1/2 times a negative 1/2. So our vertical tangent line here is x equals to negative 1/4. Then we do the last one. Find the equation of x when theta is 4 pi over 3. So we plug that in, 1 plus cosine 4 pi over 3 times cosine 4 pi over 3. And you're going to see that the cosine value here is the same as above, so we're going to get the same answer. X equals negative 1/4. And we don't need to repeat that because we already have that one. So we have two different equations for vertical tangent lines. Now the reason why there are two of them and not really three separate ones of them is because this graph, if you didn't know already, is the graph of a cardioid that has symmetry with respect to the polar axis. And the vertical tangent lines that we're identifying are these. So these two here on the left-hand side are both x equals to negative 1/4, and the one on the right-hand side crosses at x equals to 2. So we're going to finish this up and look for the horizontal tangent lines, and that's going to be y equals 2. So we have to evaluate y when theta equals pi over 3. So that's 1 plus cosine pi over 3 times sine pi over 3. So cosine pi over 3 is 1/2, and sine pi over 3 is radical 3 over 2. So I end up with 3/2 times radical 3 over 2. So y equals to 3 rad 3 over 4. That is one horizontal tangent line. Then we proceed to do the exact same thing with the remaining two angles, 5 pi over 3 and pi. So cosine 5 pi over 3 is negative 1/2, and sine 5 pi over 3 is radical 3 over 2. Oops, negative radical 3 over 2. So I'll have 1/2 times a negative radical 3 over 2. So my equation is negative radical 3 over 4. And my last one, when theta equals to pi, I have 1 plus cosine pi times sine pi, and sine of pi is 0, so I just have y equals to 0. I want us to find when the graph r equals to 2 cosine 3 theta is at the pole. That's kind of like asking for x-intercepts and y-intercepts. In this case, I want to find when the graph is at the pole. So now, do you recall from before when a graph is at the pole? Well, that's going to occur when r equals to 0, because when the radius is 0, you're at the pole. So we're going to set this equal to 0, so 0 equals 2 cosine 3 theta, and we need to solve this. When is the cosine of 3 theta equal to 0? Now this is a multiple angle problem that you have to solve, so this brings us back to trig stuff. Cosine is your x-coordinate, so your x-coordinate is 0 at pi over 2, 3 pi over 2, and so on. So basically pi over 2 plus pi k, where k is an integer. But I need to solve for theta, so instead I'm going to divide by 2, or I'm going to divide by 3, and get pi over 6 plus pi over 3k. So my multiple angles that I have are pi over 6 plus, let me add this as a 2 pi over 6 instead. So I'll get 3 pi over 6, which is 1/2 pi. And then if I add another one, I will have 5 pi over 6. So this is when my graph is at the pole, the angle theta at which this occurs. Now another question, I want to find the equation of the tangent lines. At the pole. So basically, I want to find the equation of the tangent line when theta equals to pi over 6, pi over 2, 5 pi over 6, what we had listed and found above in part A. So I want to find the equation of the tangent line. That means I have to have the slope and then a point. So back up to earlier when we were discussing slope, dy dx is dy d theta over dx d theta. And I'm going to go ahead and write out what our slope formula is going to be by using y equals to 2 cosine 3 theta sine theta, which is our r sine theta, and x equals to 2 cosine 3 theta cosine theta. Remember, this is r sine theta and r cosine theta for x and y. So that means our dy dx, following the product rule, should be negative 6 sine 3 theta sine theta plus 2 cosine 3 theta cosine theta all over negative 6 sine 3 theta cosine theta minus 2 cosine 3 theta sine theta. So there's our big long slope calculation. And I want to know what dy dx when theta equals pi over 6, pi over 2, and 5 pi over 6. So let's plug those in. We're going to have negative 6 times sine pi over 2 times sine pi over 6 plus 2 cosine pi over 2 times cosine pi over 6 all over. So if you notice, I'm just plugging them in. And some of you guys will be good enough with your trig that you won't have to write them all down, but I am on this very first one. So sine pi over 2 is 1. Sine pi over 6 is 1/2. And cosine pi over 2 is 0, so I don't even worry about that other part. Sine pi over 2 is 1. Cosine pi over 2 is rad 3 over 2. And cosine pi over 2 is 0, so again I don't need to worry about that second half. So what I have here is negative 3 over negative 3 radical 3, or 1 over rad 3. So this tells me that our slope at the pole when theta equals pi over 6 is 1 over radical 3. So because we're at the pole, I know that my equation y equals to mx plus b is 0 because I'm at the pole. So the equation of the line that I need is y equals to 1 over radical 3x. So what we need to do to finish off this problem is to calculate the slope just like this for each of the other two remaining angles. So when theta equals pi over 2, we're going to plug it in to this up here at the top. Okay, so we'll have negative 6 sine 3 pi over 2 sine pi over 2 plus 2 cosine 3 pi over 2 cosine pi over 2 negative 6 sine 3 pi over 2 cosine pi over 2 minus 2 cosine 3 pi over 2 sine pi over 2. Now at pi over 2, which is 0? The sine value or the cosine value? The cosine values are going to be 0, so I don't need either of those. Sine 3 pi over 2 is a negative 1. Sine pi over 2 is a positive 1. Cosine pi over 2 is a 0. So now look what just happened. I have 0 on the bottom, which means it is undefined. So what does that mean when the slope is undefined? It means you have a vertical tangent line, so it's x equals to 0. So then we'll do the very last one, calculating the slope at theta equals to 5 pi over 6. So we'll have negative 6 sine 5 pi over 2, sine 5 pi over 6 plus 2 cosine 5 pi over 2 times cosine 5 pi over 6 all over negative 6 sine 5 pi over 2 cosine 5 pi over 6 minus 2 cosine 5 pi over 2 sine 5 pi over 6. Okay. Now which of these are 0? Any of those? Cosine 5 pi over 2 will be 0. And sine 5 pi over 2 equals to 1. And so we're left with sine 5 pi over 6, which is 1/2, and cosine 5 pi over 6, which is negative radical 3 over 2. So sort of cleaning this up a little bit, we have negative 6 times 1/2 over negative 6 times negative radical 3 over 2. I can cancel. The 2's cancel as well. So I have negative 1 over radical 3. So this is my slope going through the pole. So I know I have the equation y equals to negative 1 over radical 3